Okay, here's the recording in progress. So we'll go ahead and begin. All right, so I'm in 11.9. I wasn't supposed to do 11.9 until next week, but I'm already there. So we're quite a bit ahead. So let's see how it goes from there. And tomorrow is our quiz. We only have 3 days this week, Monday, Tuesday, Wednesday. That being the case, your quiz is tomorrow. I hope the quiz is fairly easy. In fact, you're going to get a question today on the homework that's going to be sort of like the quiz. Okay, and then have a happy Thanksgiving. We're off Thursday and Friday. Okay, and some other reminders. So we have quiz 11, quiz 12. I am going to plan right now for the next exam to be literally on Thursday the 9th, just in case, because it looks like I'm far enough ahead. We can just have the tests on this day, in which case the following day would just kind of be an office hour. Again, I'm not promising I'll have your exams ready by the next day, hopefully by the weekend, but again, you will have the solutions video. So if you're going to study for the final exam, study off the solutions video anyway. It doesn't really matter then when I give you the exam, although I'll try to give it back to you by Monday. Okay. Then the week of the, what would be the 13th, that's final exams week. We don't have any regular meetings. If you have other final exams, check with your other instructors, of course, but our final exam, Friday the 17th of December, that's less than a month now. And it's from 8:10 to 10:40. So you'll join the Zoom as normal, but you get 2.5 hours to do the final exam. And if you say, how do I study for the final exam? Just look at the old exams. Okay, so you'll be reviewing the first test, second test, third test, fourth test, and fifth test for the final exam. By the way, yeah, bring polar graph paper. There's a chance, I'm not promising I will, but since you will need to be ready for the entire final exam, of course, part of it was polar graph paper. So have polar graph paper in case I ask you a question on polar coordinates, right? And I do have office hours during finals week. Not on Monday because I'm giving another final, but Tuesday, Wednesday, Thursday, that would be, if I have the dates right, the 14th, 15th, and 16th of final exams week from 8:10 to 10. You can join with the Zoom, the usual way that you're joining the Zoom. These are, of course, optional if you have any questions leading to the final exam. And the final is on the 17th from 8:10 to 10:40, and then we're done. And everybody have a nice holiday season. Okay. All right, so we're doing 11.9. And there's only 2 sections left, 11.10, 11.11, and I have 2 weeks to finish that all. And I think we're good. Okay. So here we go. Some reminders of where we were. So you definitely want to have this on your cheat sheet, page 768. That's section 10, but we're doing some of it even now. So I would say these first 5, power series. What is a power series? An infinite polynomial. 1 over 1 minus x. That's your basic geometric series. A over 1 minus r. Okay. E to the x looks like this. Sine x, cosine x, inverse tangent of x. Okay. One of the homework problems today involves inverse tangent. Okay. Your quiz tomorrow is going to involve sine and cosine. It's going to be almost identical. In fact, even easier, in my opinion. Of course, my opinion for how to do math isn't the same as a typical person's naturally, but I still think it's going to be easy. Okay. And I don't know how you feel. I think these are startling results. It is really weird that you can get sine by doing this, cosine by doing this, inverse tangent by doing this, and so on. Okay, so if you're wondering, how does a calculator behind the scenes, how does this guy do sine or cosine? Okay, well, here is a way. This is not the only way, so I'm not saying your calculator does it literally this way, but it is a way to do sine, cosine, inverse tangent, and so on. If you look at all this, everything here is adding, subtracting, multiplying, and dividing. So we have a very, very rudimentary calculator. So all it does is plus, minus, times, and divide. Okay, and so, well, I've got a better calculator that does sine, cosine. Look carefully, it's all still plus, minus, times, and divide, right? Everything here is adding, subtracting, multiplying, and dividing. Adding, subtracting, multiplying, and dividing. Put them in the right combination, you get sine, cosine, inverse tangent, and so on. Yes, the other trig functions there are tangent. I mean, an easy way to get tangent is to figure out the sine, then the cosine, and divide it, obviously. And then for the other trig functions, you can just reciprocate. Okay. How does the calculator do e to the x? Here is a way to do e to the x, right? And so on. And then keep in mind our geometric series, right? Okay. So a basic geometric series, a over 1 minus r. A is the first term, r is a common ratio, and we're doing that over and over and over in this section. Okay. So put this on your formula sheet. For a geometric series, the infinite sum is a over 1 minus r, provided r in absolute value is less than 1, which means r is between -1 and 1. And that leads to radius of convergence. And we could do interval of convergence, but don't feel like it right now. All right, so last time I did up to 7 star. And let me work on some more. Let's look at 13. 13 is a good illustration of differentiation term by term. Show you that. So several parts to 13, page 757 looks like. Okay, use differentiation to find power series for 1 over 1 plus x squared. And then part B, 1 over 1 plus x cubed. Part C, x squared over 1 plus x cubed. Okay. So here's a strategy. 1 over 1 plus x, treated as 1 over 1 minus a negative x. So by the geometric series, the numerator is the a, the first term, and the common ratio is the thing after the minus sign right there. So the first term is 1, common ratio is negative x. So 1, then I keep multiplying by negative x plus x squared minus x cubed plus x to the 4th minus x to the 5th. Okay, now, our ground rules, we said, is in your final answer. In general, you don't have to write the summation stuff, but I want you to write at least 4 terms. So that's my ground rules. Okay, so every time you write an answer with a series, at least 4 terms plus ... obviously. So like this. Now, it looks like I'm contradicting myself. I'm putting 1, 2, 3, 4, 5, 6 terms here. Okay, but I'm actually looking ahead. Remember, we said your final answer has to have at least 4 terms. So 5 or 6 is acceptable. I know I have to go out to 1 over 1 plus x cubed in my final answer. What happens when you differentiate a constant? 0. So when I differentiate this, I'm going to have 5 terms left. When I differentiate again, then I'll have 4 terms left. Okay, if I only started with this, if I differentiate one time, I'll lose the 1, right? Then I'll only have 3 terms left. If I differentiate again, I only have 2 left. That's way too cheap. Okay, so it's almost like every time you differentiate, you're going to lose a constant. So you want to add 1 more term just to be sure of satisfying my rule, the Melvin-Hahn rule, of writing down at least 4 terms of your final series. And yes, these are infinite series, so you should put the ... It does not stop, right? This goes on forever. All right, now I will differentiate both sides. So I'm trying to find a power series representation of 1 over 1 plus x quantity squared. And you can do that by differentiating 1 over 1 plus x. So I differentiate both sides. 1 over 1 plus x prime is 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th prime. Okay, let me work on the left-hand side. This is like 1 plus x and a -1, whose derivative is -1 plus x and a -2, or -1 over 1 plus x quantity squared. Okay, so I'm putting that back up to the top now. -1 over 1 plus x squared is equal to differentiate all of these. Derivative of that is 0, -1 plus 2x minus 3x squared plus 4x cubed minus 5x to the 4th. Looks like that. Okay. Now I just multiply both sides by -1, because in the question it asks for the power series representation of 1 over 1 plus x squared. So we look at 13b. They just want 1 over 1 plus x. Oh, sorry, 13a. 1 over 1 plus x squared. I've got negative. So just multiply by -1, which means all these signs change. So final answer for part A, 1 over 1 plus x squared is 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the fourth plus dot, dot, dot. The radius of convergence is 1 because the original radius of convergence is 1. Right? A over 1 minus r. R is between -1 and 1. So negative x is between -1 and 1. But if negative x is between -1 and 1, then x is also between -1 and 1. Now, for the next part, they want an expression for 1 over 1 plus x cubed. Part B. So I differentiate again. And by the way, before I put the book down, if you look at B and C, to go from B to C, you just multiply by x squared. The only difference is that there's an x squared in the numerator. So I'll take the answer to part B and just simply multiply by x squared. Right, so that's equal to that. Differentiate both sides. So what's the derivative of this? Again, you probably don't want to do the quotient rule. It's easier to think of it as 1 plus x and -2 prime. That's -2, 1 plus x and -3rd, or -2 over 1 plus x cubed. And then differentiate this term by term. Notice I've written down 5 terms. When I differentiate again, that's going to get lost. I'll have 4 terms, which is the requisite number that I require when you give answers for me. So -2 plus 6x minus 12x squared plus 20x cubed. That's -2 over 1 plus x cubed. In the homework question, it asks for 1 over 1 plus x cubed. So I simply just divide by -2. And very conveniently, all of these are even. So divide by -2, I've got it. 1 over 1 plus x cubed. Divide all these guys by -2. 1 minus 3x plus 6x squared minus 10x cubed plus dot, dot, dot. Okay. This tells you don't have to write the summation notation if you don't want to. What's the radius of convergence? Still 1. Right. So we said before, if a particular series has a radius of convergence r, when you differentiate or integrate, you still have the same radius of convergence of r. You don't necessarily have the same interval of convergence. Okay, these two endpoints that we talked about before, they might switch from converge to diverge, or they might stay the same. Anything's possible. Okay, so that's that. Part C, it just asks for x squared over 1 plus x cubed. All you do is multiply both sides by x squared. So that's just x squared. That's 3x minus 3x cubed plus 6x to the fourth minus 10x to the fifth plus dot, dot, dot. So there we go. What's really happening now, folks, is for a lot of our functions that are continuous and differentiable on their domain, you can replace them by these infinite polynomials. Okay? I mean, it's really weird to think that this is equal to this, only for a radius of convergence of 1, though. Okay? But this is way easier to deal with, right? We like polynomials. We can graph polynomials easily. These are very easy to differentiate. These are very easy to integrate. These are not easy to differentiate. These are not easy to integrate, but these definitely are. Okay, now let me show you 15, which is a much more convoluted problem. ln 5 minus x. Okay, I know that ln comes from integrating something that looks like 1 over 1 minus x. Okay, so to do 15, I'll integrate something that hopefully is familiar. So I want ln 5 minus x. I'm going to start with 1 over 5 minus x. Why do I start with this? Because that kind of looks like a over 1 minus r. And then how do I go from here to here? Integrate. Yeah, back to this problem again. I want to emphasize that when you differentiate all these terms, the constant drops away, right? So if you think of how many times do I have to differentiate, then add one more term to the 4, right? So this particular problem, I had to differentiate twice, and I realized every time I differentiate, I lose a constant. So I had to start off with 6 terms. Because after I differentiate, that one's going to go away, right? So you only have 5 terms. Here they are. And then when I differentiate one more time, I'll have just 4 terms. And there it is. I have 4. Okay, so that's what I mean by when you're doing the problems for me on the homework, quiz, or exam, at least 4 terms for your final answer. 2 is a little bit too cheap. 3 is a little too cheap. 4 terms, I can confidently say, okay, you know what to do, just follow the pattern. And don't forget to put the ... if it's required, right? These are series, you should put the ... Okay, the polynomial doesn't stop there. It's not 4th degree. It's infinite degree, right? All right, so 1/5 minus x. I'm not supposed to have a 5, I'm supposed to have a 1. So we played that game yesterday. Factor out the 5. So it's going to be 1 minus, if I multiply by 5, I divide by 5 here, x over 5. Okay, so temporarily, if you ignore the red, 1/5 parentheses 1 minus x over 5 is the same as that. And if you want to convince yourself of that, just simply multiply it out. Okay, the top is still 1. Multiply at the bottom. 5 times 1, 5. 5 times negative x over 5 is negative x. And now, in order to use this formula, I don't want that 5 there. Just simply divide top and bottom by 5. Okay, again, you're allowed to put a sample problem like this on your cheat sheet. Okay, say, I forgot exactly what to do. Just put a sample problem. Okay, and yes, a reminder, if we were meeting face-to-face, you'd have to memorize this algorithm. Okay, sorry. But and I say that because maybe your next teacher is going to insist that you memorize all this stuff. Anyway, so that's gone. That's 1/5 over 1 minus x over 5. So this weird looking thing is the same as this. If you're not convinced yourself of that, multiply top and bottom by 5. 5 times 1/5, 1. 5 times 1, 5. 5 times that is negative x. Okay, but when it's written like this now looks exactly like a over 1 minus r. See, I had to force my expression to look exactly like a over 1 minus r. So the first term is 1/5. The common ratio is x over 5. Careful, it's not negative x over 5. The formula already has a minus sign. So whatever comes after the minus sign is your ratio, x over 5. So multiply this by x over 5, you get that. Multiply that by x over 5, you get that. Multiply that by x over 5, there it is. Okay, so here are the first 4 terms of 1/5 minus x. What is the radius of convergence? Well, x over 5 has to be between -1 and 1. If you multiply everything by 5, then x is between -5 and 5. So my radius of convergence is 5. All right, so now I have 1/5 minus x. Now I integrate both sides, term by term. Okay. So I integrate 1/5 minus x, which is the same as this stuff. And this is the integral of 1/5 minus x over 25. This is very easy to integrate. Right? Okay, so this side becomes ln, negative ln absolute 5 minus x. There should be a negative, right, by the chain rule. Negative equals, okay, this is an indefinite integral, which normally means you need a plus c at the end. Well, how do you put something at the end when there is no n? Put it at the front. C plus, then you integrate 1/5 x, x squared over 2 times 25, x cubed over 3 times 125, x to the 4th over 4 times 6, 25, and so on. I have to turn the page to clean up the algebra. So I have negative ln absolute 5 minus x is c plus all this. Okay, so all I did from here, I did 2 times 25 is 50, 3 times 125 is 375, 4 times 625 is 2500. There it is, and there's a negative. Now multiply both sides by -1, because in the problem they want it not negative ln, just ln. Okay, I'm going to have a negative c, but we talked about this before. Negative c is still just c. But all of these become negative. Negative, 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 right? And we saw this theme before. I dropped the bars. Okay. Why did I drop the bars? The radius of convergence was 5. We're centered at 0. That means I can only be plugging in stuff between -5 and 5. If you look at this expression, If I plug in something between -5 and 5, it's always positive. Okay? If you plug in 5, you get 0, but that's not even defined. But if you plug in 4.999999, that's positive. If you go to the other extreme, if you plug in -5, 5 minus -5 is positive. Okay, so if I pick any number between -5 and 5, this thing cannot be negative, so I drop the bars. So it's C minus 1/5 x, minus 1/50th x squared, etc. Now to find the C, I plug in 0. That's typically the trick for something like that. Plug a 0 here, that's ln 5. Plug in a 0, these are all gone, right? So you have C is equal to natural log of 5. So that does it. So here's my final answer. Natural log of 5 minus x is ln 5 minus 1/5 x minus 1/50th x squared minus 1 over 375 x cubed minus 1 over 2500 x to the fourth, and etc. Okay, so that's that. So what's so good about having that? It looks like a polynomial, albeit infinite. Right? We are less comfortable with ln. You know, this ln is this mysterious, nebulous concept. Okay, but this is just like a polynomial. Very easy to differentiate, very easy to integrate. Okay. 21 star. This is x over x squared plus 16. Your 21 looks like x squared over x squared plus 1. Very, very similar. In fact, I just gave you one step. Rewrite this as x over 16 plus x squared. Factor out the 16. So it looks like 16 times 1 plus x squared over 16. And then I just say etc. So treat this as minus a minus x squared over 16. That's my hint. And how to get rid of 16, divide top and bottom by 16. I'm willing to write that in, especially since this is a starred problem anyway. Yeah, think of this as 1 minus a negative x squared over 16. So negative x squared over 16 is my common ratio. Okay, 23. I will just give you the setup. And this is the actual problem, I believe. Same in both texts. ln 1 plus x over 1 minus x. Treat this as ln 1 plus x minus ln 1 minus x, etc. How do I get this? I integrate 1 over 1 plus x. How do I get this? I integrate 1 over 1 minus x. You have to watch out a little bit about the chain rule for that one. Okay. Right, so now that we're equipped with this power series stuff, we can do some more integrals that we could not do way back in our integration chapter, such as 25. Okay, so evaluate the indefinite integral as a power series. What is the radius of convergence? Okay, so 25. T over 1 minus t to the 8th dt. The radius of convergence is 1. This is a over 1 minus r. So r is t to the 8th. T to the 8th has to lie between -1 and 1. If t to the 8th lies between -1 and 1, then so does t. So the radius of convergence is 1. Okay, now, if you think back to our integration chapter, we didn't know how to do this. Well, we could do it if this was t to the 7th. Then I could just do a u substitution, right? Like this, the only way to do it is with these power series. So it's like, I can't do this in the traditional fashion. I can do it if you allow for this infinite polynomial stuff. Okay, a over 1 minus r. So I rewrite it as the first term is t, then I keep multiplying by t to the 8th. So t plus t to the 9th plus t to the 17th plus t to the 25th plus dot, 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 dt. Okay. When you integrate, you don't have to worry about putting an extra term in there because none of these get lost. It's only when you differentiate that you have to add one more term. Okay, so again, when I integrate, I have 4 terms. I can just leave it as 4 terms. I don't have to do an extra one. And you'll see that by the answer. When I differentiate, okay, so back in this problem, I solved from the get-go, I had to differentiate twice. So I needed 6 terms at the start, 1, 2, 3, 4, 5, 6. Because every time I differentiate, I lose a constant, right? So if I differentiate, that's going to have 5 terms. If I differentiate again, that's only going to have 4 terms. No such concern when you integrate. When you integrate, just leave it as it is. So here we go. C plus t squared over 2 plus t to the 10th over 10 plus t to the 18th over 18 plus t to 26 over 26 plus dot, 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 stop. Okay, so can I integrate this? Yes, sort of, if I'm allowed to do this infinite polynomial thing. And there it is. And this only works if t is between -1 and 1. Okay, 29 star. You're 29, x over 1 plus x cubed. It should work in a similar fashion. 1 over 1 plus x to the 5th dx. They want you to integrate to 6 decimal places. This cannot be done by traditional means. I could do 1 over 1 plus x. That's an ln. I can do 1 over 1 plus x squared. That's my arctangent. 1 over 1 plus x to the 5th. Only way is by doing this power series stuff. So treat this as 1 minus negative x to the 5th. So that means the first term is 1. I keep multiplying by negative x to the 5th. 1 minus x to the 5th plus x to the 10th minus x to the 15th plus dot, dot, dot from 0 to 0.2. Okay, so I integrate x minus x to the 6 over 6 plus x to the 11th over 11 minus x to 16 over 16 plus dot, dot, dot from 0 to 0.2. Even though there's infinitely many terms, what happens when you plug in 0 to all of them? They're all 0. So I just plug in 0.2 here, 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 and here. If you plug in 0.2 here, 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 and here, it looks like this. Okay, what kind of series is this? Hint, plus, minus, alternating series. They're alternating. Are the terms decreasing in absolute value? They sure are. And do they approach 0? They sure do. And 0.2 is a fraction. That's 1/5. 1/5 to the 16th is very small. Okay. And then by the alternating series estimation theorem, it says if I stop anywhere, the error is no more than the next term. Now, I want my error to be less than 10 to the minus 6, 6 decimal places. Okay. If you punch this in a calculator, it's about 2 times 10 to the negative 9th power. Okay, I'll try to show you that. 0.2 raised to the 11th divided by 11. 1.86, I rounded it up to 2 times 10 to the minus 9. 0.000000002. So I could just add up 2 terms. So adding up 2 terms is not fair. You're supposed to add up infinitely many terms. Yes, the alternating series estimation theorem says your error is no more than this. So just have to add these up. 0.199989 is my answer. Okay, I was just going to do one more and then I'm done. I was going to rehash this tomorrow also. So, but I want you to at least see it in preparation for tomorrow's quiz. Okay, question 33. The last one here. Compute arctan of 0.2, correct to 5 decimal places. Okay, and by the way, right now, make sure you're in radian mode, not degrees. So let me double check. I'm in radian mode. Yep. Okay. Arctan of 0.2. Sorry, I messed this up. Okay, so look at the formula for arctangent. X minus x cubed plus x to the 5th over 5 minus x to the 7th over 7. Okay, and a side note, look at the sine function just above. I don't have any hands where I can point it to you because I have to hold up the book. But look at sine x and inverse tangent. They almost look the same. I mean, ordinarily, I mean, think of trig. In trig, you say sine, arctangent, and they're not close at all. Well, take a look. Their power series are exactly the same, except for the sine, you got factorials. Inverse tangent, you don't, right? See, inverse tangent, not tangent, inverse tangent. X minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. Sine goes x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7th over 7 factorial and so on. Okay, so strangely enough, the only difference between the sine and inverse tangent is the factorials, but that's beside the point. Yeah, arctan of 0.2, I plug in 0.2 everywhere, and sorry I messed up, but this is 0.2 minus 0.2 cubed over 3 plus 0.2 to the 5th over 5 minus 0.2 to the 7th over 7. Okay, now this is about 1.8 times 10 to the negative 6. I messed up a lot here, big time, but 0.2 to the 7 divided by 7. 1.8 times 10 to the minus 6. That's less than 10 to the minus 5, 0.00001. So all I have to do is add up these first three terms. 0.2 minus 0.2 cubed over 3 plus 0.2 to the 5th over 5. Okay, it's about 0.19740. And it's double check. The inverse tangent of 0.2. 0.197395 means 0.19740. Okay, so I know I ran through that fast. I'll slow down and show it to you tomorrow, but I wanted you to at least get a feel of what's going on in tomorrow's quiz. Tomorrow's quiz, you're going to be doing something exactly like this with the sine and cosine. You have much easier numbers, okay, and I want you to verify it on your calculator also. Okay. All right, but that's about it for today, folks. So let me stop the share and see if anybody has any question, and if not, we'll call it a day. So where's my chat thing? Okay, any questions, please? All right, so that's it for today. Tomorrow, I'll give you your quiz and continue lecturing, and then that'll be it. All right, okay, have a good day, everybody. Bye.
All right, take care, Professor.
Here, bye.